Hello everyone. In today's lesson, we're going to be looking at section 9.1 on correlation and the correlation coefficient. So in this section, we're going to be studying how to describe what type of relationship or correlation exists between two quantitative variables and how to determine whether the correlation is significant. Graphically, this relationship can be described by drawing a line called a linear regression on a scatter plot. The linear regression line fits the points as closely as possible. You can think of it as a best fit line. But how do we determine if a relationship exists between our variables? So data in this section is going to be represented in this form. X sub I, Y sub I, where X sub I represents our independent or explanatory variable, while Y sub I is going to be our dependent variable or our response variable. So we'll often refer to it as the response variable. So this is independent or our explanatory variable. It's what explains the change that's going on. And then we have our dependent variable. It depends on the independent variable, or it's the response variable. It's the response to whatever we're changing in the explanatory variable. So a correlation is just a relationship between two variables. This data can be represented as our ordered pairs x, y, where x is the independent or explanatory variable, and y is the dependent or response variable. On this, you can see a couple examples of what a scatter plot might look like. So if you look at the one in the top left, you'll see that it's pretty closely together. You could actually probably put a line that cuts through it, and it will describe it pretty well. So for example, we'll have something like this. You got a bunch of little dots like this, and they can be described by what's called a best fit line. And this would be our linear regression that we're going to be using to describe this best fit line for these dots on our scatter plot. If you look at the scatter plot in the top right, you'll see that there's not really a good way that we could describe what's happening by cutting this with a line. The bottom left is just like the top right, except for now this one, the dots seem to be going in a negative direction. So in this case, we'll have a negative slope on our linear regression. So the first one, we had a positive correlation. The third one, we have a negative correlation. Now let's look at this last one at the bottom right. You'll see in this slide that the dots do seem to have some sort of pattern, some sort of relationship. As x changes, y changes. But in this case, it would have a low correlation because correlation is specifically looking for a linear relationship, right? So linear just meaning using a line. So if we were to cut this with a line. So in this bottom right one, while this might represent something like cyclical change, for example, something like the business cycle, or it could be some sort of like sine wave relationship, it wouldn't have a linear correlation because there's no way that I could cut this with a line to describe the relationship as x changes, how does y change, right? In this one, as x changes, how does y change? And this is what we're looking at whenever we are looking at a correlation. We have a positive correlation, means that as x gets bigger, y also gets bigger. We have a negative correlation. As x gets bigger, y gets smaller. So now, before we actually start looking at how we're going to find this correlation, let's talk a little bit about scatterplots. So a scatterplot is just going to be a graph of ordered pairs, and we're going to put each of those ordered pairs as a dot on the graph. So for example, you would have some x1, y1, x2, y2, and so on and so forth up to xn, yn. And then on your scatter plot, for each one, you would figure out what the x and y is, and you would put a point. Let's say x2, y2 is here, and let's say that x3, y3 is here. And you would do this for every data point we have, creating your scatter plot. Our independent or explanatory variable x will be measured on this horizontal axis. So this is going to be our x-axis. Our response or dependent variable will be on the y-axis, the vertical axis. A scatter plot can be used to determine whether a line that is a straight line correlation exists between two variables. So basically what we're saying is, as this x value changes, is there some relationship with the y value that changes in a linear fashion, meaning that as x goes up, does y seem to go up in some certain amount? Or as x increases, does y seem to go down by some amount? And can this be described by a line, hence the linear relationship? I do want to note here, though, that non-linear relationships or correlation between multiple variables can exist. Multicollinearity refers to a situation in regression, which is what we're doing when we create this line. It's called a linear regression. So it's a situation regression analysis where two or more independent variables are highly correlated with each other. And this can actually cause a lot of issues with a lot of different models, because when we have multiple independent, that's our x variables, correlated with each other, and we're doing multivariate analysis, meaning more than one variable, this can make it very difficult to determine what's causing this change in y, right? If they're both related to each other, as one goes up, the other seems to go up, as one goes down, the other seems to go down, well, which one's causing the change in y? Or how much are each of them changing y? And this is why, for example, multicollinearity can be such a big issue for a lot of models. So now, let's talk about how we construct our scatter plot. So the first thing we're going to do is you're going to label your x-axis, whatever your explanatory variable represents. This could be the height of people that you meet on the street. It could be the amount of time you're waiting between eruptions for Old Faithful at Yellowstone National Park. And then you're going to want to scale this based on your data. So for example, if you have whole numbers where it's like 1 to 10, then you would want to probably put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you have values that are in hundreds of thousands, you might want to do like 100,000, 200,000, 300,000. You would need to scale this based on whatever the data is that you are actually going to be graphing. Then you want to label your y-axis, your response or dependent variable. So as x changes, what is changing going up or down on my vertical axis? And again, you would want to scale this based on whatever your data represents. Next, you're going to want to put a title on your graph, because without a title, anyone who's looking at this is going to have a hard time figuring out what exactly it is that this graph is showing them. You want your graph to be as self-contained as possible, so that if I look at your graph, I can see the x-axis and what its label is, I can see your y-axis, what the label is, and the title of the graph. And then from there, I should be able to determine what is this graph showing me and what does it mean. Now, once you put this title, this is where you're then going to have your data, and you're going to put a dot for every single data point that you have. Okay, for our first example, I've written out here the GDP of certain countries in millions of dollars and their CO2 emissions. And we're going to create a scatter plot to see what this looks like and determine if it looks like there might be some relationship between how much GDP a country has versus how much they emit in emissions of CO2. So first thing we're going to do, we're going to draw our XY axis. So our x-axis is going to be our independent variable. That's going to be the GDP of these countries. So we're going to label this GDP. And then we need to figure out what sort of scale we're going to use. So looking at these numbers, you can see that it looks like the lowest number we have is about 0.9, and the largest number we have is 4.1. So in this case, I'll probably just do it in terms of 1, right? So we'll have that. This would be a GDP of $1 million. Put millions here. 2, 3, 4. Now our y-axis is going to be our CO2 emissions. So it's our CO2. And if you look at this scale, this seems to be in the hundreds up to a little over 1,200. So in this case, what I'm going to use for scale is I'm going to use something like 200. So this would be 200 tons. This is in tons. 400, 600, 800, 1,000, and 1,200. And then from there, what we're going to do is we're going to look at each of these data points. So in this case, this is my x, this is my y. So x1, y1 would be 1.7, so it'd be something like this. So x1, y1 would be 1.7, 620.1. So this is what it would look like if you had it in terms of x, y. So we're going to go over on our x-axis to about 1.7. We're going to go up to 620. So somewhere about here, and we're going to put a dot. Then we're going to go to 2.4, and then we're going to go up on the vertical axis to 457.6. So 2.4 is about here, 457.6 about here maybe. Next one, 3.0, and then 457. So this one's, sorry, this actually should be a little higher. This one's going to be 3.0, 457. Next one is going to be 1.2, 389. So we go to 1.2, we go to 389, be about here. 4.1 to 810. So 4.1 goes to 810. We have 2.3 has a value of 332.9. 0.9 has a value of 235. 1.8 has a value of 297.8, so about 298. 2.9 has a value of 413.9, so 2.9, 413.9, somewhere about here. And 3.4 has a value of 1,216.5, so it's going to be somewhere about here, and we're going to put a dot here. So this would be what our scatter plot looks like, and this is what we're going to be trying to determine if there's a best fit line that describes this, showing that there might be some correlation. Now, if we didn't have this last one, it does seem like there's a pretty decent linear relationship, and this is why when we talked about previously about outliers, outliers can actually lead to a lot of issues, because if I didn't have this one, I could probably describe this pretty well with a linear relationship. Well, what this is going to do is it's going to pull up this correlation line, and it's going to make it so it doesn't fit quite as well as it would without it. But this data is correct, so we would just have to deal with that. Here we have another example where we're looking at, does the amount of hours that someone does an exercise affect GPA? So in this case, our independent variable, what we're going to be looking at changing is the number of hours exercising. The dependent variable, or response variable, is going to be the GPA. Does GPA change based on the amount of exercise somebody does in hours? So we're going to start again by drawing our x and y axis. Our x-axis is the amount of exercise in hours. So we'll put exercise, and I'll just put a little parentheses, hours. And then the y-axis is going to be their GPA. And then for title, I'll just put something like exercise versus GPA, right? But you might want to put something a little more catchy, like does exercise impact GPA, something like that. Okay, so now what we're going to do is we're going to figure out our scale. Looking at our amount of exercise, it looks like these go anywhere from 0 to 18. So what I'm going to do is I'm going to do jumps of 2, but make my intervals kind of smaller so they can all fit. So this will be 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, I may have made it a little too small. For our GPA, it looks like this will go anywhere from 0 to 4, which makes sense because it's a GPA. So I'm going to make the scale a little bit bigger just so we can kind of see how much it's really changing. But it's going to go in terms of 1. So GPA of 1, 2, 3, 4. Now this is something you also need to kind of consider when you're looking at the scale of your x and y. Because notice the amount of exercise is going to change for anywhere from 0 to 18. But the GPA is only changing from 0 to 4. Meaning that we're going to see, because the way I drew this, a lot bigger jump. Going from 1 hour of exercise to another is half of this little interval here. Going up by a whole GPA value is quite a jump. So it's going to be basically kind of stretched out vertically. And this is something you have to be careful about when you're making graphs, because you can make something, for example, if you're looking at like stock charts where it's going up, 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 maybe, you know, if you scale it like this, it looks like it's going almost straight up. Whereas if you were to like compress a little bit, scale up the x-axis, now it looks a little flatter. So just something to consider when you're doing your scale is also what would make it make sense for what you're actually trying to show. Okay, so first one, we had the person exercised 12 hours and has a GPA of 3.6. We go over to 12, go up to 3.6, and we put a dot. Next person exercised 3 hours, has a 4.0 GPA. Next person exercised 0 hours and has a 3.9 GPA. Next person exercises 6 hours, has a 2.5. Next person exercises 10 hours, has a 2.4. Next person exercises 2 hours, has a 2.2. Next person has 18 hours of exercise, has a 3.7. Next, we have someone who exercises 14 hours and has a 3.0. Someone who exercises 15 hours has a 1.8. And last, we have a person who exercises 5 hours has a 3.1. So now, looking at this data here, does it look like there's a best fit line that kind of describes this, right? Does it seem like as exercise increases, that your Y, your GPA would also increase, or as X increases, maybe your Y decreases? It doesn't really look like it. If I were to try to fit this with a best fit line, it would probably be something like this, which isn't really giving us a high correlation either in the positive or negative direction. So in this case, it doesn't really look like there's much of a correlation between how much one exercises and their GPA. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.